in the last video, we were trying to determine the eigenvectors for this matrix as well as the corresponding eigenvalues. And so far, we've determined the eigenvalues to be 2, 3, and -5. Then what we did was we took this eigenvalue, and as we explained in the previous matrix, we subtract it from the diagonals of our original matrix to give these numbers. And now this new matrix that we formed by doing that times some vector we want to set equal to the 0 vector. And why we do it like this, that we explained in video number 15. Okay, now what we want to do is solve for x1, x2, and x3, and that will give our eigenvector that corresponds to lambda equals 2. So we have this now in augmented matrix form. And remember from our previous videos now, if we had this written out in full as a set of 3 simultaneous equations, then this column here would be the coefficients of x1 in those 3 simultaneous equations. This would be the coefficients of x2. This would be the coefficients of x3 in those 3 simultaneous equations. So x1, x2, and x3. Okay, let's get into row echelon form. The first thing we can do is we can switch these 2 rows around. So this will, the 0, 0, 0 will be in the bottom row, and then 3, 1, -5. And if we multiply the top row times 3 and add to this row, that will make that 0. So the top row stays unchanged. And this becomes 0. 3 times 0 is 0, so this is just 1. And 3 times 4 is 12 minus 5, that's plus 7, and we have zeros all the way across. Okay, we can stop right here. We look at the matrix and we see that x1 is a lead variable, x2 is a lead variable, and x3 is a free variable. So what we do now is what we've done in the previous videos. We express the lead variables in terms of the free variable. So x1 and x2 are lead variables, and x3 is the free variable. Now from here then we just have x2 plus 7 times x3 equals 0, or obviously x2 is equal to minus 7 times x3. And from here we have that from the top part we have minus x1 plus 4 times x3 equals 0, so x1 equals minus 4x3. And that's all we can say about them in terms of specificity, because x3 can take on any value that we want it to. So the vector here then would look like we have x3. This is minus x1, wasn't it? We have minus x1 plus 4 times x3 equals 0, so x1 should equal plus 4 times x3. Get rid of this minus sign. Okay. Now, so the eigenvector is x3, that's the free variable. x2 is minus 7x3. And x1 is plus 4x3. So there's the corresponding eigenvector, we can take the x3 out. That will equal x3 times 4 minus 7, 1. So this is the eigenvector. This and any constant times this eigenvector will also be an eigenvector. We discussed in the first video that if you have an eigenvector for a matrix, if you multiply that eigenvector by a constant, it's still an eigenvector. And here we can say we can multiply by any constant because x3 is a free variable. It can take on any value that we want it to. It could be 1, 2, or negative 1,000 if we want it to be. But here then is the eigenvalue, and it can be multiplied by any constant. So we'll just take it as being multiplied by 1. So what we have right now is when lambda equals 2, the corresponding eigenvector is 4 minus 7, 1. So we have found one of the eigenvectors. Let's continue along. Now we want to look at what happens when lambda equals 3. Okay, now first thing we need to do is make some space. Now for this matrix, remember it's this one, but we subtract lambda off of the diagonals. So here we're going to have 1 minus 3, that's negative 2, 0, 3, 0, 2 minus 3, that's negative 1. Here's 1, 4, 0, and here we have negative 3 minus 3, that's minus 6. Okay, let's write an augmented matrix form. We have minus 2, 0, 3, 0, minus 1, 1, 4, 0, 6. Like this. And remember, this is an x1 column, an x2 column, an x3 column. And let's see, what can we do here? Well, we always want to make this 1, so let's divide this through by minus 2 on the first row. That'll give us 1, 0, minus 2. Like this. And let's see, let's just interchange these rows here. We have 3, 1, 6, and 0, minus 1, 0. Now if we multiply this by negative 3 and add it to this row, what do we get? So the first row doesn't change. Negative 3 plus 3 is 0. And times 0, 0, that stays as 1. And here we have, this was minus 6 here, so it should be minus 6 here and minus 6 here. And then we're multiplying across by minus 3, so that gives us plus 6, so this is 0. We can multiply this by negative 1. So we end up with this, and we can stop right here. We can see that x1 is a free variable. Actually, x1 is a lead variable. x2 is a lead variable. And x3 is going to be a free variable. So, and again, what we do is we express the lead variables in terms of the free variables. But here for x2, clearly x2 is going to be 0, because here we have 0 times x1 plus x2 plus 0 times x3 equals 0. So x2 is 0. x3 is the lead variable. It could be anything that we want it to be. So we have x3, x2 equals 0, and now we go back up to here. We have x1 minus 2 times x3 equals 0. So 1, or x1, is equal to 2 times x3. Okay, so with our vector here, x3 can be anything. That's 0. That's 2 times x3. So that would be the eigenvector. x3, 0, 2 times x3. One, 0, 2. So the eigenvector corresponding to lambda equals 3 is this, or any multiple of that 1. So we found now the second eigenvector. So we go to write it down. Lambda equals 3. And the eigenvector is 2, 0, 1. So we found 2 of the 3 eigenvectors so far. Let's go ahead then and find the third one. And for that, we have lambda equals -5. So what we have to do is same procedure as we've been doing all along. First we can erase this stuff. And now we're going to have, for these entries, 1 minus -5, that gives us +6. 2 minus -5, that gives us +7. And here we have -3 minus -5, that should give us +2. Okay, and this times this vector we want to come out to be equal to 0. So let's see what we have. Let's write an augmented matrix form. Like this, as we've done in all the previous videos, starting right with the first video actually. And again, these columns here, if we had this written out as 3 simultaneous equations, then this would be all the coefficients on x1, these would be the coefficients of x2 and x3. Okay, and let's see. Let's take this up to the top first. So we have 3, 1, 2, beneath it 6, 0, 4, and then here 0, 7, 0. And let's see, if we multiply this by -2, we can add it to that one. So let's see what we have. The top row stays unchanged, of course. Three times -2 is -6, so that comes out to 0. -3 times Negative 2 times 1 is negative 2, plus 0 is negative 2. 2 times negative 2 is negative 4, plus 4 is 0. And this is always, this is going to be 0 now. And then down here we have 0, 7, 0. But actually we can stop right here. Okay, again, x1 is a lead variable, x2 is a lead variable, x3 is going to be the free variable. And again, we can see that x2 is going to have to be 0. Because here we have x1 plus 7x2 plus 0x3 equals 0. So x2 has to be 0. x3 can be anything. That's the free variable. So we have x3, x2 equals 0. And then up here we have 3 times x1 plus x2, but that's 0, plus 2x3 equals 0. So bring this over to here, and we have x1 equals minus 2/3 x3. Remember, what we do is we always express the lead variables in terms of the free variables. So there's x1, x2, and x3 that we were solving for. So let's just make some room. Okay, so we have x3, that can be anything. x2 is 0, and minus 1, or x1 is minus 2/3 x3. Or we can take the x3 out. Here and we have 1, 0, minus 2/3. And there's the eigenvector. Now, if we want to, remember this can be anything. And remember, as we said during the previous video, an eigenvector times a constant is still an eigenvector. So we could multiply this by 3. And we would have negative 2, 0, 3, and that would still be an eigenvector. And remember, x3 can be anything. So once you have an eigenvector, you can multiply it by any number, and it's still an eigenvector. So for lambda equal to minus 5, we'll just keep it in a regular form like this, as we had to begin with. But it doesn't have to stay like that if we don't want it to. Minus 2/3, 0, 1. So there you have it. 3 different eigenvalues with corresponding eigenvectors. And that was for this matrix right here. So as you can see, it takes a while to do the number crunching. Also, for this problem, when we were determining values of lambda, we had a cubic polynomial. We could factor out a 2 minus lambda, so make it easy to solve. But if you have polynomials now that are cubic or higher powers, and you have to factor them to find lambda, that can be rather difficult. But there's a process you can use called synthetic division that makes that a lot easier. And if you can go to the website here at digital-university.org, click on the calculus videos and scroll down them, and you see that we have a section there called synthetic division, where we explain the technique, and we have many examples there as to how it's used. Because for every one of these problems that involves eigenvalues and eigenvectors, to determine lambda, the eigenvalues, you're going to have to solve some sort of polynomial set equal to 0. In that process there, synthetic division can be very helpful. Okay, that's it for this video. Come back for the next video. We're going to talk about diagonalization.